Hello, in this video I'll be showing you exactly how to do all the different types of proof by induction questions that may show up on your A-level further maths exam. I've put timestamps for all the different types if you're struggling with a particular type in the description below, so feel free to sort of skip around the video based on what you know and what you don't know. Without any further ado, let's get into how to solve the general proof by induction question. So the very first thing you need to do is you need to prove that the statement is true for n equals 1, which is our base case. So firstly, you'll prove it for the base case, then keyword assume. You'll assume the statement to be true for n equals k. This is an assumption. And then using this assumption, you will prove that the statement is true for n equals k plus 1. Right? So if you can manage to prove that the statement is true for n equals k plus 1, assuming that is true for n equals k, then you've essentially proved by induction that whatever the statement is claiming works, right? That's the whole sort of logic behind proof by induction questions. Now that you sort of know the logic behind general proof by induction questions, today I'll be going through the four most frequent types of proof by induction questions that come up in A-level further maths exams, starting by proving summations. So you've all probably seen this formula. It's the summation of r squared. It equals n plus 1 and 2n plus 1 over 6. So we'll start off with proving this, which should be quite interesting because all of you have probably used it through your formula booklet, or you will use it through your formula booklet. So it's good to know why it sort of works, right? So following the general steps of solving a proof by induction question, we start by looking at our base case. So in our base case, firstly, we'll look at what's happening at the left-hand side when n equals 1, right? So when n equals 1, then our left-hand side is just r squared, which is just 1 squared, which is just 1, right? And our right-hand side is 1 times 2 times 2 plus 1, 3 over 6, which is 6 over 6, which is just 1. So as you can see, LHS equals RHS. Therefore, we've proven it could be true for the base case, which is n equals 1, right? So when n equals 1, the left-hand side equals the right-hand side, hence this formula or this equation works, at least for the base case for now. So after we solve the base case, we assume it to be true for n equals k. Assume true for n equals k, right? What this means is that if we were to swap out n for k in this equation, essentially all you do every time you see an n, you just swap it out for a k. So k here will equal to k plus 1, 2k plus 1 over 6. Notice how it's the exact same thing, but every time I saw an n, I swapped it out for a k. That's essentially what we mean when I say, or what I mean when I say n equals k. Assume true for n equals k. So we're just assuming that the summation of r squared from r equals 1 to k is this. We're assuming this to be just straight up true. Okay? Now that we have assumed this, let's look at what n equals k plus 1 might be. Okay, so r equals 1, r squared, k plus 1. What actually does this mean? If you don't know anything about summations, right, let me sort of try and explain this to you. So all this means is that it's going to start off with 1 squared, because it's r squared, then it's going to add 2 squared, 3 squared, and so on and so forth, until we get to k minus 1 squared plus k squared plus k plus 1 squared, right? That's all the summation of r squared means, from r equals 1 to r equals k plus 1. Now, if you notice very carefully, 1 squared plus 2 plus squared plus 3 squared plus 4 squared, so on and so forth, until k squared, isn't this just the summation of r equals 1 r squared to k, right? We can just write this as a summation of this plus k plus 1 squared, right? And notice how this looks very, very familiar to this, right? So you can already probably guess what's happening. We're going to substitute k plus 1, 2k plus 1 over 6 for the summation of r squared till k. So k plus 1, 2k plus 1 over 6 plus k plus 1 squared. Okay. Now, the trick is going to be, we're trying to prove that this initial equation, right, is true for k plus 1. So what we want is, instead of n plus 1, what we want to get to in the end, this is really important, is we want to get to something like k plus 1, and then k plus 1 plus 1. Essentially, every time there's an n, we want that to be k plus 1. 2k plus 1 plus 1 over 6. So if we can get to this, assuming this, we essentially win. That's our victory condition, okay? So I'm hoping that once we expand and simplify this, we'll end up with this. Okay? And exam technique, or just a general tip, every time you're doing this question, always think, like, what am I trying to get towards? Because I know I'm trying to get towards this. I'll just try and make my life as easy as humanly possible, right? So let me just normalize the fractions. K plus 1, 2k plus 1, right? Plus 6k plus 1 squared all over 6. Now, I notice I can take k plus 1 out. So k plus 1, this is already a great start, right? 2k plus 1, and we're left with 6k plus 1 here. All over 6. So k plus 1, let me expand out the brackets. 2k squared plus k plus 6k plus 6, right? Over 6. Now factorizing, this is already looking really promising. The first time it's supposed to be k plus 1, right? So factorizing 2k squared plus 7k plus 6, you will end up with, what will you end up with? I think you should end up with 2k plus 3 and k plus 2 maybe? Does this work? 6, 2k, 7k, no, sorry, 4k plus 3k, 7k. Yeah, this does work. Cool. Over 6. Oh, and now, as you can see here, because I know what I'm trying to work towards, I know exactly what I need to do. So the numerator is just k plus 1 and then 2 times, right? This is nothing but 2k. Okay, let me do this step by step. 2k plus 2 plus 1, right? And this is nothing but k plus 1 plus 1, right? All over 6. So if you notice now, this looks something like k plus 1 and then 2k plus 1 plus 1 and then k plus 1 plus 1 over 6. I don't know why I did over 2 there. But we got it. So we started off with r squared, r equals 1 to k plus 1. And we've ended up with, assuming that r squared to k is true, because we substituted this in, we've ended up with something that looks exactly like the formula we're trying to prove, right? You're not done here though. If you stop here and prove my induction question, you'll actually get marked down. What you need to write in the end is a victory statement, essentially, saying that because, I'll write down for the first time, it's true for n equals 1, right? And assumed that it's true for n equals k So when we assume that it's true for n equals k, it's true for n equals k plus 1, right? Therefore, whatever this is, you can literally just copy and paste this. Like, I might even just be really cheeky because I don't want to rewrite all this, and I literally just move it down manually. These questions don't tend to be like logically too hard. It's just a lot of working, as you can see, right? Therefore, this, whatever you're trying to prove, is true by induction. And in fact, for all 6 of these things, this will be a victory statement. So I've written this down here. I'll probably make a separate bookmark or timestamp, whatever it's called, for the victory statement. But in all of the other questions that I'll go on from now on, I'll just write victory, because that's what my teacher used to do, so it's kind of nostalgic too. But yeah, this is generally how you'll attempt summation proofs. On to the next one. This is the second type of question that I see come up quite often, which is the divisibility proof. A general question like this will be n cubed minus n, or prove that n cubed minus n is divisible by 6 for all n greater than or equal to 1. So, like any proof by induction question, we'll start by investigating the base case. Because if it's not true for the base case, it's just flat out false, right? So when n equals 1, n cubed minus n is 1 cubed minus 1, which is 0, which actually is divisible by 6, right? So our base case passes. Very nice. So, base case passes, so we assume that n equals k is true. Remember, the key word being assume. So, we're essentially assuming that k cubed plus k is divisible by 6. Now remember this. This will come in handy in the next step. So we're assuming that k cubed plus k is divisible by 6. Now let's investigate what happens when n equals k plus 1. When n equals k plus 1, n cubed plus n, I think that's what we started to, n cubed minus n. This is why, right? Always double check the question if you're not sure. So n cubed minus n again. I said plus again. God. N cubed minus n will become k plus 1 cubed minus k plus 1, right? So expanding this out, we'll get k cubed plus 3k squared plus 3k plus 1 minus k minus 1. So plus 1 and minus 1 cancel out. We'll end up left with k cubed plus 3k squared plus 2k. Okay, now looking back, here we've assumed that k cubed plus k is divisible by 6. So if we can get a k cubed by k out, we can sort of just automatically assume that it will be divisible by 6. So let's split up this 2k into k plus k. So we can rewrite this as k cubed plus k, right, plus 3k squared plus k. So I've just split up this 2k into these 2k's. Now, we already know by assumption that this is divisible by 6, right? So we only need to worry about proving it for this now. So you can also rewrite 3k squared plus k as 3k plus 1, right? What do you know about k and k plus 1? Because k and k plus 1 are two consecutive integers, if you times any two consecutive integers, it has to be an even number. So we know that k plus 1 will be some even number, will be like 2m. Right? You see where I'm going with this? Therefore, we know that 3k plus 1, right, can also be written as, can also be written as 2m. as this is just an even number, the product of two consecutive integers. Therefore, because it's 3 times 2, this is also divisible by 6. So this was already divisible by 6. Now the latter half of the sum is also divisible by 6, which means our whole sum, or k plus 1 cubed minus k plus 1, is divisible by 6, assuming that n equals k is true. So this is how you do a divisibility proof. I've linked exactly how to phrase the victory statement earlier on in the video. I'm not repeating it every time, so just go check that out. I'm sure I've timestamped it. The third type of proof by induction question I've seen is matrix proofs. In this case, you'll be given a matrix like A equals 2, 1, 0, 3. This is a 0, right? And you'll have to prove that for A of n, or A of n equals 2 to the n, 3n minus 2n, 0, and 3n, for any n that's greater than or equal to 1. And you have to prove this by induction. Now, matrices questions, just like any other questions, once you can do one of them, you can pretty much do all of them. They all have the same trick behind them. So let's start off by doing a generic proof by induction by checking the base case. So when n equals 1, right? So when n equals 1, A equals 2, 3 minus 2, 0 and 3, right? Which is just equal to 2, 1, 0, 3, which is what this is. So we know that this statement is not just a straight up lie. There's some truth to it as it works to the base case, n equals 1. This is correct. So once we prove it for the base case, you assume it to be true for n equals k. So assume it to be true. Now, what does this mean? That we assume that a to the k, basically, for this matrix will be 2k, 3k minus 2k, 3k, and 0. Right, if I'm correct in assuming what the matrix was. Here's one last look at the question, because I know I'm skipping back and forth. This question's too big to fit on one page. But now that we've assumed it to be true for n equals k, we'll try and figure out for n equals k plus 1. For n equals k plus 1, we'll do a to the k plus 1. Now, if you know anything about matrices, or the laws of matrix multiplication in particular, right, you know that a to the k plus 1 is just the matrix A multiplied with the matrix a to the k, right? And we've already assumed that a to the k is nothing but this, and we know what a is. So this multiplication can simply be 2, 1, 0, 3 times by what's happened to my pen? That's genuinely not writing right anymore. Oh, there we go. We're back. 2 to the k, 3k minus 2k, 0, and 3k. We just multiply these normally. And remember, we're trying to work towards a situation where instead of k here, it's a k plus 1. Instead of k here, there's a k plus 1. Instead of k here, there's a k plus 1. That's what we're trying to work towards. It's really handy to have what you're trying to work towards in your mind. So by matrix multiplication, we get the top left is going to be top row times the bottom row, which is just 2 times 2k. The top right is going to be the top row times the second column, right? Which is going to be 2 times 3k minus 2 times 2k. And This is all plus 3k. The bottom one is going to be 0. And then the bottom right, but the bottom left one's going to be 0. The bottom right one's going to be 3 times 3k. So I hope you can already see where this is going. 2 times 2k is nothing but 2k plus 1. 0 remains 0. We can add this 2 times 3 to the k plus 3k. That's 3 times 3 to the k, which is 3k plus 1 minus 2k plus 1 and 3k plus 1. So once again, so firstly, we proved that the base case was true. Then assuming that n equals k is true, n equals k plus 1 is also true. This means that the statement a to the n equals 2n, 3n minus 2n, 0 and 3n is true by induction for any n that are integers above 1 or equal to 1. So the fourth type of question that I've seen come up is an inequality proof. In this case, you have to prove that 2 to the n is always greater than n squared for all n that is greater than or equal to 5. So in this case, as in every case, we'll start by checking out the base case. When n equals 5, the left-hand side is simply 2 to the 5, which is 32. And the right-hand side is 5 squared, which is 25, right? So as we can see clearly, 32 is greater than 25. So the LHS, or the left-hand side, is bigger than the right-hand side. So the base case works. As soon as we see the base case working, we automatically assume true that n equals k, or we assume that n equals k is true. Now, what does this mean exactly? This means that we're assuming that 2 to the k is always bigger than k squared. Okay? So assuming this, let's look at what is the result for n equals k plus 1. So when n equals k plus 1, we get 2 to the k plus 1 is greater than k plus 1 squared, right? So this ends up being 2 times 2 to the k is greater than k squared plus 2k plus 1. Now, most of the other proof by induction questions you can sort of just algebraically do and get to an answer. This one, you have to sort of critically think a lot more. It's a lot more sort of problem solving-y. So how you actually do this one is that you use this assumption. If 2 to the k is greater than k squared, then 2 times 2 to the k is also always greater than 2 to the k squared, or 2 times k squared. That's perfectly valid, right? So what we can do is we can be cheeky and use this, because we know 2 times 2 to the k is always bigger than 2k squared. We can substitute this for k squared, because we know 2 times 2 to the k is always bigger. And this actually allows us to manipulate the equation further, right? So what we end up with is k squared minus 2k is greater than 1, which is k minus 2 is greater than 1. And once we've come to this position, for any k that is greater than or equal to 5, we can clearly see that k times k minus 2 is always going to be greater than 1, right? Always true for k is greater than or equal to 5. So we proved it. Again, the victory statement, I wrote it out in the first one. I won't repeat it again. But in case you skipped to this section, it normally goes, we proved the base case. We proved that for n equals 5, the equation holds. Then we assume that n equals k. We prove it for n equals k plus 1, assuming that it's true for n equals k. Hence, by induction, it's true for all natural numbers that are greater than or equal to 5. Or this identity is true for all natural numbers that are greater than or equal to 5. I really hope you learned something watching that video. Please do like and subscribe. And if you have any questions related to further maths, A-level maths, or A-level physics, please feel free to drop me an email on my email below. Or if you have any requests for any full guides, or if you'd like me to try a different topic and doing all the different styles of questions for a different topic, please let me know. Thank you so much for watching this video. Hope to see you again. Bye.